everybody. Happy Friday. So our speaker today is Jenny Wan, who's visiting us from Stanford. So Jenny did her undergrad at Caltech before starting at Stanford as a PhD student. She's an NSF fellow and just about to start her third year because they're on the quarter system. And she works with primarily with Risa Wexler. And she's been doing a lot of really exciting stuff sort of at the interface of theory and observations. So she's been here all week hanging out looking at JWST data. And today she's going to tell us about dwarf galaxies at cosmic noon.
Hi, like Ren said, my name is Jenny. I am a grad student at Stanford. I'm really excited to be here, to have been here all week. Boulder is great, love it a lot. Today I'm going to be talking about some of the work that I've done with Risa, my advisor, and Ren, and other people in our group, to better understand the sort of tidal evolution of subhalos and satellite galaxies in cosmological simulations using JWST observations of the satellite population at cosmic noon. Okay. Nope. Can't find the screen. Okay, cool. Okay, so as many of you probably are aware, satellite galaxies and sort of dwarf galaxies in general have been very valuable probes of cosmology and a wide range of astrophysical processes in the local universe. Historically, however, these low mass systems have been quite difficult to observe at large cosmological distances because they're so faint. But now that we have JWST, we can finally see these low mass faint companions of their more massive hosts at redshifts greater than 1 for the very first time. So the plot that I'm showing on the side here, which I shamelessly screenshotted from Ren's 2023 paper, is just showing the stellar mass and redshift distribution of a bunch of these JWST identified satellites. So those are all the little gray dots. And overplotted is the HST mass completeness limit in the solid red line of the same field. And so what you can see is that the vast majority of these new JWST observed systems fall well below the HST mass completeness thresholds. And this means that we're really entering this sort of fundamentally new regime where we now have access to these statistical samples of dwarf galaxies in the inner regions of the host halos at high redshift for the very first time. And this is super exciting because we can use these new data to test our models of cosmology and galaxy formation and sort of learn about things like the size and morphological evolution of massive galaxies, to understand the origin of galactic conformity, which is this observed relationship between the star formation properties of host galaxies and their satellites, and also to understand the relationship between dark matter halos and their galaxies in this sort of high redshift, low mass parameter space, which previously has been basically like observationally inaccessible. But before we can do any of those things in like any kind of meaningful way, we have to first really understand the systematic uncertainties that are in our models, especially given the precision of these new data. And one of the largest sources of this uncertainty stems from our limited understanding of how subhalos and the satellite galaxies that live in them evolve once they fall into the gravitational potentials of their host halos. So there's this general lack of consensus in the literature as to how quickly galaxies lose their mass to gravitational tides. Modern high-resolution idealized simulations predict that these low-mass subhalos can basically survive as these shrinking bound remnants for arbitrarily long periods of time, while hydrodynamic simulations, which include things like baryonic physics, tend to predict that this mass loss happens much faster. So what I'm showing here is a comparison between the mass loss tracks or tidal tracks, as they're called, between a prediction from a hydrosim, so that's the dashed black line, and an idealized model in the solid orange line. And if you're not super familiar with how to read tidal tracks, I'm just gonna talk about it really quickly because it'll show up a little later too. So basically the x-axis tells you about subhalo mass loss, and the y-axis is telling you about galaxy or stellar mass loss. And you could think of time as sort of progressing along the track, starting from the top right and going to the bottom left. And so what happens is, as your subhalo is orbiting its host, it's constantly losing dark matter. And for a while, the stars stay pretty intact. So this F star is 1 for like a fairly long period of time, until you reach some critical turnover point, after which your stellar mass loss increases rapidly. And what you can see is that where this turnover happens is much later in the idealized model than in the hydro model. And so what this is saying is that the idealized model predicts that that satellite galaxies don't start to significantly lose their stars until much later than what's predicted by hydrosim. And you might think, yeah.
Let's go, please.
Mm-hmm.
So it seems that the curve and the decay slope is linear. It seems like
This part?
yeah, this slope is linear.
Mm-hmm.
But the dark matter, I guess, profile, the stellar profiles are very different.
Yeah.
How can you understand what is linear?
I mean, I guess these are all like the fact that subhalos follow these sort of like defined tidal tracks to begin with is sort of just a function of how like stripping is like an outside in process where you get rid of your like less bound particles and then you like slowly peel back the layers to the inside. So it's like, I think that is part of why this relationship is the way that it is. And the galaxy profile, like the shape of the galaxy profile will affect the slope of this, but I'm not sort of dealing with that at the moment. Yeah. Yeah, so you might be thinking that this is like totally reasonable because hydro simulations have baryonic feedback, which can sort of like, it can like core out your subhalo profiles. Feedback can also accelerate disruption, stuff like that. And all of that is true, but also the sort of story of disruption is a little bit more complicated than that, which I will do next. So I guess the sort of basic picture of how this happens is your subhalo falls into the potential of its host, and then it experiences these destructive tidal forces that basically strip mass away from the subhalo's outskirts. And this process is called tidal stripping. This is a nice little video that one of my friends, another grad student in our group, made of a subhalo that is being stripped as it's orbiting the host. It's centered on the subhalo, so you're not actually seeing it orbit. But you can see, like, as time goes on, tidal forces are basically stripping, unbinding the particles from the sort of bound structure and creating these tidal tails or streams. And you can imagine as time goes on, enough of subhalo's mass might become unbound so that you no longer have like an observationally relevant system or like a bound system at all.
Do you take into account merging as well, or just stripping?
So we merging in the sense.
Because little galaxies tend to merge with each other.
Yeah, so our simulations are, well, so I guess the first thing to say is that our group uses dark matter only simulations. So we're not actually simulating the galaxies themselves. We do take into account like when subhalos merge with each other, that gets that is part of like our merger tree and halo catalog system. Yeah, so this is sort of the general picture of tidal stripping. But there are also sort of like non-physical effects that can sort of accelerate the mass loss rate of a subhalo or mimic disruption. And this is what's called artificial disruption, and it's like a fairly well-documented problem in cosmological simulations. And there are sort of two main classes of reasons why this happens. So the first is that halo finders are fallible. So halo finders are these tools that are used to identify and track your subhalos and halos from snapshot to snapshot in your simulation. And this is like quite a hard thing to do. And so they can often make mistakes. They can either like misidentify and mischaracterize your subhalo, so give like assign it an incorrect mass or something, or it can just lose the subhalo entirely, so it cannot identify the thing that is actually there. And because of this, many simulations use these orphan models, which are these sort of post-processing models that approximate the properties of your subhalo after the halo finder loses it. So it's saying like, we don't necessarily believe that the subhalo no longer exists, even if the halo finder can't find it. So we're going to do our best to like guess at what system would be there if the halo finder could find it. And then the second class of problems are these sort of numerical artifacts that come into play because in order to make cosmological simulations tractable, you have to discretize the like continuous dark matter field into particles, and this can lead to various problems. So one thing we have to do is use this numerical trick called force softening, which basically prevents too close encounters between your simulation particles. So like in the real universe, if you have like a blob of 10⁶ solar masses of things, it's not going to be able to get like arbitrarily close to another giant blob of 10⁶ solar masses of things. And so to do that, you have to implement this sort of like softened gravity law. But what this does is it also sort of smooths out subhalo profiles on the scale of this force softening length. So it smooths out your profile on these small scales, and it suppresses the central density of your subhalos. And this makes them more vulnerable to tidal stripping because you no longer have like a strong core in the same way that you would for like a real dark matter, dark matter profile. The second effect that can bias your mass loss rate is this thing called discreteness noise, which is basically like a thing that happens when your subhalo has lost enough of its particles so that Poisson fluctuations can make your mass loss rate excessively noisy. And this is particularly a problem because fluctuations that temporarily increase the mass loss rate of your subhalo can lead to runaway mass loss because it's sort of like a positive feedback loop. You lose more mass, the mass loss rate becomes noisier, and then this cycle perpetuates. And then the third main issue are these two-body like scattering events that happen between particles, and this allows for sort of artificial energy exchange between particles in your subhalo. And what this does is that it basically causes the sort of the inner regions of your subhalo to go from something that looks like a realistic dark matter profile into something that's collisionally dominated. So it just turns like the inside of your subhalo into a globular cluster, basically. And that's not like a physical thing that happens. And the size of that sort of numerically relaxed region also grows with time. So basically, once enough of your subhalo's particles get stripped, all you're left with is this collisional core that's not like a real physical structure anymore. And at that point, your subhalo is like the mass loss rate of your subhalo is no longer trustworthy or reliable. Basically, all of this is like a very long way of saying that there still exists a lot of uncertainty as to how subhalos lose mass to gravitational tides in simulations because of all of these various issues. Cool. So one of the main goals or motivations of this particular work was to improve on the modeling of these low mass, heavily stripped subhalos in our cosmological simulations. And we sort of do that in, there are like two parts. The first is this improved orphan model. So a lot of this work is thanks to Phil Mansfield, who is a postdoc, I guess now a research scientist in our group, but he did a lot of work to understand when the numerical effects that I talked about in the last slide begin to bias a subhalo's mass loss rate. And if you're interested in like the details of that work, I'll point you to his 2024 paper, which is really nice. But the basic idea is that even if your halo finder can find a subhalo, that doesn't necessarily mean that its mass and its other properties are reliable. And so what we do in our orphan model is Phil found that once the subhalo particle count falls below some limiting threshold, then these numerical effects begin to dominate and your mass loss rate becomes biased. So in our orphan model, once our subhalos fall below this limiting particle count, we replace it with an orphan subhalo. And this is, a pretty significant improvement over the sort of typically used orphan models, because in most of those models, you don't initiate an orphan until after your subhalo loses it, without really considering whether or not the subhalo itself was sort of like a realistic physical system prior to that point. And then the second thing we do is implement this flexible tidal evolution model for our satellite galaxies. So there's been a lot of work showing that the evolution of a subhalo's physical properties as it's undergoing tidal stripping really only depends on the total amount of subhalo mass that's been lost, and they follow these sort of well-defined tidal tracks. And because of that, we use this tidal track model to estimate the stellar masses of our satellite galaxies at the times like subsequent to when they fall into their host potentials. And so the particular form of the tidal track we're using, which is this sort of cut in half equation, is from the Smith et al. 2016 study, which looked at the tidal evolution of galaxies in these hydro simulations. And so here FDM is shown on the x-axis. It's telling you about the remaining bound fraction of dark matter mass post-infall. F star, which is on the y-axis, is the remaining bound fraction of stellar mass post-infall. And then this F1 half parameter is really the key parameter in our model, and it's the thing that tells us about how durable our subhalo is or how resistant to tides it is. It basically encodes like where this turnover happens in the tidal track. So if you have a lower value of F1 half, then this turnover happens further to the left, and your galaxy is more durable. And if you have a larger value of F1 half, then this turnover happens further to the right, and your galaxy is more fragile. Great. And the Smith et al. Study found that the galaxies that they looked at in their simulation were best described by an F1 half value of about 0.05. So that's the value that we use in our fiducial model. Yeah. But it's not necessarily guaranteed that all galaxies have the same value of f1/2, right? And it's probably most likely not the case because galaxies have like a distribution of sizes and a distribution of like stellar to halo size ratios, which can lead to a distribution in how quickly the stripping happens. And then the other thing is that this Smith et al. Work, this form of the tidal track was empirically determined from hydrodynamic simulations, which suffer sort of from their own set of numerics that come into play because you're simulating, typically you're simulating your stars or your baryons in the dark matter at different particle masses. And what this does is it leads to this basically preferential heating of the simulated galaxy, and it causes galaxies to be a little puffier basically than they actually should be. And this mischaracterization in galaxy size can then perpetuate into a mischaracterization in tidal stream.
Yeah, I just put the same thing. It looks like F is defined as the in terms of gas mass loss fraction, a galaxy mass loss fraction, not dark matter.
f1/2, to be like super explicit about what it means, f1/2 is the value of fdm at which f star is 1/2. So it's like the fraction of your dark matter that you have remaining once you've lost half your stars. Yeah.
Yeah, thanks.
Mhm. Yeah, so for all of these reasons, we allow f1/2 to vary between 0.001 and 0.5 in our model so that we can sort of explore these uncertainties. This range is chosen to be quite conservative. It's very broad, but we expect that it brackets sort of the true scope of f1/2, and it's wide enough to sort of encompass the range of disruption physics that's consistent with both what hydro models predict and these idealized models. So this brings me to the second part of this work, which is to assess the consistency between our simulated satellite populations and what we observe in the JWST data in this 1 to 3.5 redshift range, and then to use the sort of model framework that we've developed to hopefully place some constraints on subhalo tidal evolution. And before I get into sort of the like main results of that, I just want to briefly talk about like the specs of the data that we use basically. So the observations come from Ren's 2023 paper, uses multiband NIRCam imaging in good south since the early JWST data, and also HST imaging. The simulations we use are coming from the Symphony Group suite, which is a suite of cosmological dark matter only zoom-in simulations that look at host halos at the about 10 to the 13 Msun virial mass scale. In this particular work, we just focus on massive quiescent host galaxies and their satellite systems. And this plot is just showing you the stellar mass and redshift distribution of our host galaxies. So the green are the observed hosts, and then the sort of black and gray are our simulated hosts. Cool. So now the sort of main results. Here I am comparing the cumulative satellite stellar mass functions measured from the JWST observations. So those are the green curves, and predicted by our fiducial model. So those are the black dashed curves. And then the dark gray shaded regions are showing the range of stellar mass functions that are allowed by varying f1/2 in our model between 0.001, which sets the upper bound, and 0.5, which sets this lower bound. And what we find is that within our model framework, Varying this F1 half parameter can lead to a factor of 3 to 4 variation in the predicted satellite mass function. And this really highlights the extent of the uncertainty that gets imparted on the stellar mass function by this uncertainty in how we model the tidal disruption of galaxies. Given the sort of observational uncertainties, though, our fiducial model is consistent with the observations to within 1 to 2 sigma, basically across the board, which is interesting. There might be a little bit of a hint of a redshift evolution in this sort of durability parameter, where the data seem to prefer less durable things at lower redshift and slightly more durable things at high redshift. So you can see our fiducial model sort of over predicts the normalization here and maybe under predicts at the higher redshift. But more work definitely needs to be done before we can say anything for certain about that. And then the other thing we can do to sort of visualize the same information that's in these mass functions in a way that allows us to place constraints on F1 half.
Okay,
Yeah.
before you go.
Mhm.
It looks by eye as though those error bars are correlated, are they?
Well, these are cumulative mass functions. So basically, like anything that shows up in this mass bin is also in these mass bins. So I guess in that sense, they are, yeah.
So the discrepancies are not as bad.
Yeah. So like these like weird fluctuations like here, I think are just, yeah, it's just because of the fact that like these statistical fluctuations look like slope changes in your mass function when you do these mass functions. Yeah. So if the normalizations match and then the like lowest point sort of matches, then you can kind of assume that like anything in the middle is just statistical stuff. Noise. Yeah. Cool. So here I'm attempting to constrain the value of F1 half by sort of plotting the mass function information a little different. Here I've collapsed the first 3 redshift bins into one, and I'm just ignoring our highest redshift bin where the mass completeness limit was kind of crap. And so what I'm plotting in these solid colored lines is the average number of simulated satellites per host that fall above 10 to the 8 Msun in green and 10 to the 9 Msun in purple as a function of F1 half for galaxy durability. And then the corresponding satellite counts from the data are shown in these shaded bands. And so the idea is that the intersection between the solid line and the shaded band gives you a constraint on the value of F1 half. And so I'm showing in the dark gray dashed line our fiducial value, which is coming from these hydro predictions. And I'm also showing in the light gray dashed line a value of F1 half predicted by this specific idealized model. And I guess the main takeaway from this plot is that our fiducial model is fully consistent with the data, but also the data is consistent with F1 half being much lower than what the hydro simulations predict. So at the moment, our ability to sort of place real meaningful constraints on F1 half is a bit limited by the statistical uncertainties in the observations. So it's kind of hard to distinguish between these two models. But there is a lot of data out there, and so this puts us in a pretty good position. This whole week I've been working with Ren to basically try to expand the observational sample of satellite galaxies that we have. And so with that expanded sample, we'll hopefully really be able to hammer down on these statistical error bars in the observations And then we'll be able to use this framework to provide like real meaningful constraints on F1 half and its galaxy durability. Okay, so that brings me to my conclusions. We've implemented this flexible tidal evolution model in our simulations, and we found that galaxies are likely at least as durable as what hydro simulations predict, and possibly much more durable than that. With a larger sample of satellite galaxies, we'll be able to place meaningful constraints on subhalo durability, learn about the tidal evolution of galaxies, and the sort of relationship between subhalos and their galaxies in this new low mass, high redshift regime. Cool. Thank you very much.
Any questions?
Right now, just never look at pricing policies, are you planning to look at another option to the future?
Yeah, we're also going to be doing star forming posts in this like next part of the work. Hopefully be able to compare the two populations and see how they.
Right, just like I was asking about, do you have an idea of what differences you might see in line or?
I guess sort of the simple answer is I'm not sure. I can sort of, I mean, given the same like host halo mass, you're going to have different assembly histories for things that are star forming versus things that are already quiescent. And so, yeah, so that might have an effect. Maybe you have subhalos that have merged. You have more mergers further back in the past if you have these large quiescent systems, so they have more time to disrupt. So that might change what your satellite populations look like. The potential of the baryons that are coming from your galaxy is also going to make a difference, because if you have like a disk potential, that has been shown to accelerate disruption. And so if you have like a star forming like spiral galaxy with a disk, that might also affect things. But it's kind of hard to say because there's so many competing effects that go in different directions. So we really have to model it to figure it out.
Along those lines, do you want to speak to like what is satellite conformity, and do you think you'll be able to constrain that?
Yeah. Yeah, I guess I haven't thought too much about conformity. It's basically the idea that like the satellites around star forming hosts are more star forming, and the satellites around quiescent hosts are more quiescent. I think it's kind of it's a manifestation of assembly bias, which is basically the idea that like the assembly history of your halo is going to affect its other properties, like the star formation histories and things like that. Yeah, so this is a thing that's been observed sort of out to redshift like 1 maybe. And so we're hoping to extend those measurements to higher redshifts, see if it, yeah, I guess like if it exists or not. That's something that different cosmological models predict different things about. So that's one potential like anchor for determining what is right or not about some of these models. Yeah, and it's something that we'll definitely be looking to do in upcoming.
Yeah.
You were saying before that you're looking to extend or expand on the data that you're looking at. Is that primarily with higher redshifts, or are there other data sets that you're trying to?
Yeah, so right now we're still focusing on this sort of cosmic noon range. yeah, I mean, potentially we can go higher than that, depending on like how low in mass we can go. And there is a lot of data also at lower redshifts that a lot of people have studied. I mean, there's been a lot of work with the local universe about dwarf galaxies and stripping and stuff like that. So I guess the like ambitious plan is that we can do all the redshifts and all the masses, but yeah, for now, just this little cosmic unit slice.
Suggest there might be a connection between redshift and subhalos. Is there a connection for that?
Yeah, so I think, so one of the things that I sort of just glossed over was the fact that we like don't consider baryons at all in our simulations because they're dark matter only, and we don't have, we're not simulating like any kind of analytic potential for the galaxy or anything. And so my hunch is that this redshift evolution is because towards lower redshift, you have more contribution from the baryonic component of the halo, and so that can accelerate disruption, and I think that might be what this trend we're seeing is coming from. And so one way to figure that out is in upcoming simulations, we'll be adding in these baryonic potentials into our hosts, and so that hopefully will be able to tell us something about this.
This is somewhat related to Andrew's question, but I'm wondering if you could speak a little more on those points that appear to be all at the same and set.
Yeah, this one, this is basically saying, like, after, I don't know, whatever mass this is, like something times 10 to the 8, you have like nothing in this range and something here. And so just when you're doing these cumulative mass functions, yeah.
Say one object.
Well, these are averaged over many hosts, so there's like, yeah. So however many on average per host.
Right, any other questions for Jenny? Great, let's thank our speaker again.